Start. Okay, we are officially live. Thanks so much for joining us to everyone who has tuned in. This is the third Gen Chem Study Session with Dr. Taylor. We are so excited to have you, and we hope that you learn a lot. So without further ado, I will pass things off to Dr. Taylor.
Fabulous. Thank you. All right, so exam 3 is coming up. It is on Saturday. Oops, let's get this to work. There we go. Saturday, October 28th. We start things at 10 a.m. unless you're in the ARC room, and the ARC room starts at 9 a.m. This is going to cover Chapter 7, Chapter 8, and Section 12.2. 12.2 is properties of liquids. So depending on how smooth that transition was, you might not have even noticed that 12.2 wasn't just naturally part of Chapter 7. I know sometimes it just kind of flows right in there and you don't actually notice that it's actually a different chapter because it goes really well with intermolecular forces. I know Dr. Diekman sent out an announcement just earlier today that it's Section 7, but not 7.7 or 7.8. One of those is molecular orbital theory, which you guys have probably not heard of, and that's why, because we don't cover it. Chapter 8, we don't do 8.2, which is combustion analysis, or 8.5, and I actually didn't look up what is in 8.5. We can pull up the Alex textbook. But basically all of that's hanging out in the 701 section. So 701 has details about what all that is, but really whatever y'all went over in class is what's on the exam. So we usually rely on our lecture slides to guide that really closely. The other thing I'll mention, because I definitely got this one wrong earlier today, Dr. D's exam review that he's going to do is going to be on Thursday, a different day for goodness sakes, from 7 to 9 p.m. in our classroom, SLC 1.102. So apologies to my sections that I got that wrong. It's actually on Thursday, but he did post that earlier this afternoon. So by now you'll have already seen the fact that we do lots of multiple choice exams with 2 short answer. We're going to try to keep that general thing going on. Exam 3 overall tells a pretty good story. It is basically in 2 parts, which is Chapter 7 is all about molecules in 3 dimensions. So Chapter 7 is all molecules in 3D and some of the ramifications of that. So that's where this dealt with VSEPR, valence shell, the electron pair repulsion. This also then therefore dealt with polarity. It dealt with intermolecular forces. It dealt with properties of liquids, but this again is actually 12.2. The properties of liquids relies on intermolecular forces. Also in here is valence bond theory. As well as hybridization. And we go ahead and put in line skeleton diagrams. Line skeletal diagrams. Got Halloween on the brain. Essentially, those are the things where we can draw this and say that that's actually 5 carbons all connected together. Or we say the bends and the ends have carbon. With, of course, enough hydrogens to fulfill octets. So all of that is Chapter 7 and that 12.2. So that's one set of things. And then the other set, essentially, we start to move from molecules. And as we move from molecules, we move into dealing with chemical reactions. So Chapter 8 is dealing with chemical reactions. And as we deal with chemical reactions, this is going to be balancing. This is going to be dealing with balancing stoichiometry. which is the fancy way of saying we're going to do grams to moles conversions, but dealing with the chemical reaction in that. We'll do limiting reactant, and we'll also do percent yields, which sometimes I forget about because it's a relatively minor. After limiting reactant, percent yield is more straightforward than limiting reactant. There we go. That's what I wanted to say about that. So these are our two main topics. So one of them is all about molecules. The other one is all about chemical reactions. So in here, we're also going to have a lot of analysis of what's going on. So for example, we could talk about various molecules, but the question's always going to be is what do we actually care about in a particular molecule? So for example, if we are talking about ammonia, we now have a lot of different questions that we could ask about this molecule, and we'll have completely different answers. So we could ask what is, I'll make this larger in just a moment, the electron domain geometry. If I could spell this, there we go. And let's go ahead and make this larger so we can actually see it. There we go. But we could also ask what is the molecular geometry. We could ask about the intermolecular forces. But we can now also ask about the hybridization of the nitrogen atom. We could also ask now how many sigma bonds, sigma and pi bonds are in the molecule. And we could also ask how many electrons are in hybrid orbitals. So one of the challenges of this unit is the fact that we now have a lot of different ways of talking about molecules. So before, when we were doing Lewis structures, we still had different things we could ask. We could ask about a formal charge. We could ask about resonance. We could ask about bond order. We could ask a lot of different questions, but oftentimes they built on one another and they were connected to each other in some way. Some of these are connected to each other. Some of these are not. It just depends. But I'm going to go ahead and just walk through these since I now came up with like 6 different questions to just talk about ammonia. So I'm going to go ahead and do this part. So I want to know about the electron domain geometry. What I'm going to do is I'm going to count my number of electron domains. So for electron domains, I'm going to count lone pairs, and I'm going to count bonds. And the weird thing sometimes about an electron domain is that a single bond and a double bond, it doesn't matter. They count the same. It's just an area where there's electron density. So for this molecule, I have got 1, 2, 3, 4 electron domains. So if I want to know about my electron domain geometry, is 4 electron domains. So that electron domain geometry is tetrahedral. So y'all will need to have all of those memorized. So that is stuff you need to commit to memory. It will not be anywhere else except for your brain. So that is stuff you need to know. When it comes to the molecular geometry, this is the part now where I'm going to care about lone pairs. So I have this lone pair here on the top, and that's going to change from my electron domain geometry, and my molecular geometry will be different because of the lone pair. So because of that lone pair there, this is actually going to be a trigonal pyramid. So this does still have a 3D shape associated with it, and that lone pair still matters for what 3D shape it has, but because it's a lone pair and not a bond to another atom, we're going to name it differently than we name the electron domain geometry. When we come around to intermolecular forces, remember intermolecular forces are always between molecules. So this is always about what's happening between molecules. Can't really read that word very well. So I always like to draw another one. So if we're going to talk about intermolecular forces, then I want to think about, well, what happens if I have another one of these and another one of these? What's going to be the interactions in between the molecules? And when I think about that, I've got this beautiful lone pair here, and there's nothing else to cancel out my lone pair. So this molecule is definitely going to be polar, which means it's also going to have a dipole moment. So because of that, we are definitely going to have, so my intermolecular forces, I'm definitely going to have dipole-dipole interactions. So I've got a partial dipole-dipole. So I've got a partial negative charge where my lone pair is, a partial positive charge where all my hydrogens are. So they're going to line up essentially like little magnets. I'm going to have dipole-dipole interactions. Because I have dipole-dipole interactions, I want to take a moment and think, do I have a hydrogen covalently bonded to a nitrogen, an oxygen, or a fluorine? And I do. So this connection in between hydrogen and that lone pair is actually not just a dipole moment, it's a special kind of dipole moment that we call a hydrogen bond. And that really is because of the covalent bond, but the intermolecular force of hydrogen bonding is still an intermolecular force. So we do have hydrogen bonding, still an intermolecular force in between molecules, in between the molecules. And lastly, don't forget, even though it's not as strong of an intermolecular force, we do, because there are electron clouds, we do still have dispersion forces. So sometimes, so either called London dispersion or dispersion forces, but we do have those as well in here. So all of those are our intermolecular forces. Hydrogen bonding is the strongest of this set, then dipole-dipole, and last London dispersion. But all three of those will contribute to how these molecules interact with each other and how they're attracted to each other. Next up, the hybridization of the nitrogen atom. So this is going to connect very closely to my electron domain geometry. So these two things, while the terminology will be different, they should, the process to get there will be similar in the fact that for hybridization, I also care about the number of electron domains. So we already figured out that there were 4 electron domains for the nitrogen atom, but now what the hybridization of the nitrogen atom means is now I care about things like sp, sp2, sp3, those sorts of things. So now I need to think about how many electron domains do I have, and therefore, what's my hybridization? Now I still have 4 electron domains. That's still true. So that did not change. So I still have 1, 2, 3, 4 electron domains. Those are all still there. So because of that, this is actually going to be sp3 hybridized. So my nitrogen atom should be sp3 hybridized because it has 4 electron domains. So that reminder that when we talk about hybridization, what we are essentially doing is we are combining orbitals together. So because I'm going to basically mix 1s and 3p orbitals together to get my sp3 orbitals, I'm looking for 4 electron domains. So I'm looking for 4 hybrid orbitals in the end, but we name them for all of the atomic orbitals that we combined to get there. So 1s orbital, 3p orbitals to get to sp3. I also asked about sigma and pi bonds because I was on a roll. I didn't ask about bond angles, so that's okay. There's a lot of things we could ask about this one little molecule. When the review started, the person was a little bit worried because we didn't have that many people in the waiting room, and we usually have more folks waiting on the Sundays. Thank y'all, by the way, for being here on a Monday afternoon. Sorry about that. That's my schedule problem. But I was like, don't worry, I got this. We could talk about ammonia for like a half an hour. Let's go ahead and go down the list. So we did hybridization based on electron domains. Next up, we're going to do how many sigma and pi bonds are there. So keep in mind, we just care about the bonds here. So I'm just going to worry about the fact that all I have are single bonds. So because all I have are single bonds only, that also means that I'm only going to have sigma bonds. So if that's all I have, I'm only going to have sigma bonds. And this is going to be the same number. So I have 1, 2, 3 single bonds. 1, 2, 3. So since I have 3 single bonds, I also have 3 sigma bonds. When we're talking about a sigma bond is just going to be the overlap. Here's a hybrid orbital, and here's my hydrogen. So I can do this. There we go. Overlap. So we typically refer to this as head-on or direct overlap, because 2 orbitals are just coming right at each other. So since I have 3 single bonds, I am in fact going to have 3 sigma bonds. If I was going to have pi bonds, I would need double bonds. I don't have, or triple bonds. So double bonds or triple bonds would get me pi bonds. I don't have either one of those here. So I just have sigma bonds. So it's just the same number of single bonds as sigma bonds for this particular molecule. Again, if we had double bonds or triple bonds, numbers would be different. So just to give a quick example of that with a small molecule, we could look at this one, and we could still count all of our sigma and pi. So in this case, if I want sigma, I'm going to go off of the fact that for every single bond, I have 1 sigma. And whenever I have a double bond, I also get 1 sigma. And if I had a triple bond, I would have 1 sigma bond. So because here in this molecule, I have 1, 2, 3 bonds total, I would have 3 sigma bonds. Then my pi bonds, a double bond is going to have 1 pi bond. A single bond will have no pi bonds. A triple bond will have 2 pi bonds. So here I do have, in fact, 1 double bond. So this one would have 3 sigma bonds for each one of the single bonds and the double bond. And it would have 1 pi bond from the 1 double bond. So I can still count sigma and pi, but we were doing ammonia, and ammonia doesn't have any double bonds or triple bonds. So it was a little not as interesting in sigma and pi, but we can still do it. So as long as it's got some sort of covalent bond, we can assess for sigma and pi bonds if we'd like to. Back to ammonia. How many electrons are in hybrid orbitals? Ooh, this is a little bit more. So how many electrons are in hybrid orbitals? So what I want to think about is I want to think about the fact that between the nitrogens and the hydrogens, my hydrogens, we're going to assume are actually not hybridized. Those hydrogens only need to form 1 single bond. So when I'm thinking about my hydrogens, scroll down for a moment. When I think about hydrogens, I've got that little 1s electron, and this actually works just fine. So there's really no reason to hybridize hydrogen. It's going to do just fine being atomic. So the 3 electrons that hydrogen brings to ammonia, not hybridized. So you could keep in mind that whenever we are talking about ammonia, I'm just going to redraw it from scratch. We can either count the electrons that we see here in bonding. We could also count valence electrons from ammonia. So a reminder, we could always do it this way. How messy is my periodic table? Oh, I didn't check this before I got started. Whoopsies. I do just use the same OneNote file from exam review to exam review, but I did mean to make sure that my periodic table was clean. But I got distracted because my tablet that I used to write with needed to be updated. So good news, I updated the software of my tablet. Bad news, I now have a clean periodic table. Okay, good. So my nitrogen's gonna have 5 valence electrons, hydrogen's gonna have 1 for each one of them. So I'm trying to think of what could be in my hybrid orbitals. I want to consider the fact I've got 5 valence electrons from nitrogen and 3 from each hydrogen. We just talked about the fact that as far as hydrogen is concerned, there's no reason to hybridize hydrogen. It's going to be just fine. So out of all the valence electrons that I have, 5 from nitrogen, 3 from hydrogen, I now really only need to think about the 5 from nitrogen. The other thing is, because the nitrogen is hybridized, it's going to have things in hybrid orbitals. So we were talking about that notion of things being sp3 hybridized. And if we think about this, we should have electrons. So here, 1, 2, 3, 4, 5. Okay, good. What we're looking for is we still need 3 electrons that are in orbitals by themselves, so they could potentially form bonds. So here I have 1, 2, 3 electrons alone in orbitals for bonding. And that is what we need because we have 3 single bonds. So I need 3 electrons from nitrogen ready for bonding. And then I have this set together. This is not a bond. So this should be a lone pair. This should actually be a lone pair. So if this is correct for my hybridized nitrogen, I should have 1 lone pair on nitrogen and then 3 bonds. And when we look at our structure, that's exactly what we have. So I do in fact have my 1 lone pair that does go into hybrid orbitals. And then I have 3 lone electrons ready for bonding. So out of all the valence electrons that could possibly be in hybrid orbitals, all of the electrons from my hydrogens, all 3 of those, are just in atomic orbitals. So these are in atomic orbitals, so these don't count for our hybrid orbitals for hydrogen. And then the other electrons from nitrogen, actually all 5 of those will be in hybrid orbitals. So when I scroll back up to figure out where my original question was, how many electrons are in hybrid orbitals, that actually is just going to be 5. 5 electrons are in hybrid orbitals. So I've been talking for not quite a half an hour. Oh, I'll go through bond angles real quick. What are the bond angles? I'll ask for questions after I do bond angles. There's 2 different ways we can ask for bond angles. If we just ask for bond angles, and that's the only thing that we say, or what are the bond angles, you should assume that we mean the actual bond angles. So if it just says, what are bond angles? I wish we would have phrased it better than that. But if that's what it says, we are going to go with that less than 109.5 degrees. So from a tetrahedral geometry, we would know that we would be dealing with the 109.5 because this is trigonal pyramid. That is what would give us that less than 109.5. Our lone pair on our ammonia is going to basically push on the bond angles through the rest of the molecule, and they're going to repulse against those single bonds, which is going to shrink the bond angle in between my hydrogens to be less than 109.5. So it just asks you what are the bond angles. We're looking for less than 109.5. The other question we sometimes ask is what are the ideal bond angles? So that's the other question that we can ask. what are the ideal bond angles? The word ideal really just is going to bring in the idea that we're not going to worry about the lone pair, essentially. We're still going to remember the lone pair for our electron domain geometry, but in this case, we're just going to think about the fact that a tetrahedral electron domain gives us 109.5, and then we just wouldn't worry about the less than or the greater than. That tetrahedral will give us 109.5 for our bond angle. So that's the other question that we can ask about ammonia. So my point in all of this is when we talk through chapter 7, we can talk about almost any topic in chapter 7 with the same molecule. So the good news is if you're looking for practice in chapter 7, any molecule that we've ever drawn that has covalent bonds, you can go through and ask some of the exact same questions with. So you can even go back to some of the Lewis structures that we drew back in chapter 6 and ask some of these same questions. What's the electron domain geometry of the central atom? What's the molecular geometry of the molecule of the central atom? What's the hybridization? What are the bond angles? What intermolecular forces does it have? Almost all of those questions work beautifully for most of the molecules that we've drawn the whole time. All right, so now that I've talked for almost half an hour, but not quite, do we have any questions in the chat so far?
We have quite a lot of questions.
Great.
Yeah. So the first one is, what exactly causes bond angle deviations? Is it just lone pairs or also multiple bonds?
Okay. What else?
Can you go over bond polarity between elements and ways to remember how to find this? Can you also explain dipole movements?
Okay.
What would hybridization look like for a single atom, for instance, carbon and phosphorus? Can you explain the correlation between vapor pressure and intermolecular forces? Why does a greater IMF have a lower vapor pressure? Can you explain what an induced dipole and instantaneous dipole is and what their difference is, or for us to essentially focus on? Can you explain the correlation between surface tension and greater intermolecular forces? Does it mean that because we have a greater IMF, we then need more energy to increase the surface area? Essentially, what is the reasoning behind it? Can you go over questions that involve balancing chemical equations with moles and the varying methods there are? Also ones involving mass gram to produce an exact product. How does lone pair and double triple bond affect angles? Can the follow-up video include how to solve the sample exam 3 questions 4, 6, 9, 10, 11, 15, and 26? What kind of math equations will be on the test? There are many different equations and just want to make sure I'm focusing on the right ones. Will it be the same kind of math that we saw on exam 3 practice test, or will it be the ones in the end of chapter questions? In a follow-up video, can you go over questions 4, 6, 10, 13, 15, 25, and 26 on exam review 3? Can you explain what a London dispersion is and how it is different from the other intermolecular forces / how to determine it? Are bonds only considered nonpolar if it's between C and H and diatomic molecules? How do we know when to consider hybridizations, or do we assume all molecules contain hybrid orbitals? Will we be tested on knowing how to draw hybrid and sigma pi orbitals? And the last question is, how do you do balancing equations for more complicated chemical equations?
Okay. Anything else right now?
That's it for now.
Fabulous. Great. Okay. So going in kind of a wonky order, because some of these are close to yes/no questions. So as far as drawing hybrid orbitals, the short answer, I actually haven't looked at what anybody else has requested, but I got to go with God, I hope not, which really, honestly, is I would fight against making y'all draw hybrid orbitals. I don't know if any of y'all have seen me try to draw hybrid orbitals, because I'll take a shot at the sp orbital because it kind of looks like that. But once you get out of 2 dimensions, drawing hybrid orbitals is awful. So for drawing hybrid orbitals, I would say if we asked you to do that, we'd only do SP and SP2 because those are the ones that are flat. But even then, honestly, the only thing I would really worry about is the fact that in a hybrid orbital, most of your electron density is on one side versus the other. So the fact that here I have something really lopsided, this is the side towards the bond, erase, there we go. This is the side towards the bond. So I wouldn't worry about having to draw them, but I would understand the fact that your hybrid orbitals are supposed to reflect the VSEPR bond angles. So hybrid orbitals are only really there to put electrons back in orbitals in geometries that we already saw in VSEPR. And that essentially you've got 2 lobes, but the large lobe is always towards the bond. It's always towards the other nucleus. To basically say that we expect more of the electron density to be towards the other nuclei, towards other atom in the bond. Actually drawing it like you guys did before, no, like we haven't really had to deal with the orientation of these. So I wouldn't worry about that a lot, but I would worry conceptually about like what's trying to reflect, and it is trying to reflect a greater electron density in the bond. So that part is there. This one, bonds being nonpolar, for the most part, so this is the part where I know I bother some people about this, but really for bonding, really you just worry that this, a carbon-hydrogen bond is nonpolar, and then anything that is towards itself is nonpolar. So a carbon-carbon bond is nonpolar, a fluorine-fluorine bond is nonpolar. Anything to itself, the same atom. While if you did have your entire chart of polarity values, you would see that that's not entirely true. But basically for where we are, we're essentially going to assume that unless it's a carbon-hydrogen bond or the exact same atom, those are the 2 times we're just going to assume it's nonpolar. All the other times we're going to assume it's a little polar. And that is an assumption that we make because we don't give y'all the values of polarity. We're basically just asking you to look at a periodic table and figure it out. I do think that was a question someone else had, was how to deal with polarity. Yeah, how to deal with bond polarity. Oh no. See if we can fix this. Okay, good. So dealing with bond polarity. So when we deal with bond polarity, the thing that we're really trying to deal with is part of this does go back to chapter 6, where we took a look at the fact that fluorine is our most electronegative atom. And so we basically kind of looked at fluorine and then we were like, all right, the closer you get to fluorine, the more electronegative things are across the periodic table. So we would say things like oxygen is very electronegative, and then chlorine, and then nitrogen, and then sulfur. So the idea of electronegativity really is that idea that's kind of related to things like electron affinity, where if you have electron density, so this is a hydrogen bonded to a fluorine, and I want to draw the electron cloud around it, that fluorine is going to pull most of the electrons. This is supposed to be my electron cloud. The fluorine is going to draw most of the electrons towards it. So thinking about the fact that fluorine is the most electronegative on the whole periodic table, And the goal of fluorine is basically to get as much electron density around it as possible. Is going to make this bond basically be lopsided. There's going to be more negative stuff, more electron density on one side than the other. So since I have more electron density on one side than the other, this is going to create for me a partial negative charge where there's more electron density because electrons are negative, and a partial positive charge where that hydrogen is. So the fact that this is there, and because it's a fluorine and a hydrogen, that being said, because like in the bond, this is always going to be the case, that fluorine is always more electronegative than the hydrogen. That also means that I'm going to have a dipole moment on this bond, technically also this molecule, the entire time. So the notion that I have, so a dipole moment is just a way, it's another way of saying that I always have this partial negative and partial positive charge. I always have the partial negative and partial positive charge. So the dipole moment is another way of saying that my molecule is basically a little magnet and has a positive side and a negative side all the time. So when we just say, hey, my molecule has a dipole moment, an overall dipole, that's that partial positive, partial negative part all the time. So hopefully that helps with that reminder about electronegativity. Fluorine's more electronegative. I know I wound up covering up the chlorine underneath it. So this does go back a bit to chapter 6 stuff. So if you wanted a more description or you wanted to read more about electronegativity, all that's back in chapter 6, where we did bond polarity. So bond polarity is actually back in chapter 6. That one. That one. So when we talk about dipole moments, there's a couple of different things to deal with in dipole moments. So realizing that we have a lot of different shapes to deal with. One of the things to think about when we deal with dipole moments. So if, for example, I had a linear molecule, but I had A's and X's. So some weird atom in the middle, A, and I have that fluorine on one side, very electronegative, and I have my hydrogen on the other. My hydrogen's not very electronegative, but my fluorine is. So here I would have a dipole moment towards my fluorine, and maybe a little one that maybe it goes this way, maybe it goes that way, I don't know. Between the A, which we don't know what it is, because I'm trying to avoid having to deal with completing my octets right now. But basically, we would assume that this would not cancel out. We would assume that there would be some dipole moment here on the left that would be different from the one on the right. And so we would wind up with the molecule having an overall or net, let's respell that, an overall or net dipole moment. For the entire molecule. So overall or net dipole moment, because those don't cancel each other out. So because I would have two dipoles that are different from each other, they don't cancel out. However, if I had a different molecule, here's a fluorine and here's a fluorine, and it's still linear. Now I would have a dipole moment for each of my two bonds, and because they're the same, but in opposite directions, these would then be, these would cancel. So I have polar bonds, but a non-polar molecule. So you can have polar bonds, but a non-polar molecule is definitely possible. As far as how to analyze, a lot of this, there's a couple of things to consider. So there's ways to try to make this simpler, but one of the things I need y'all to keep in mind, none of this things with polarity is one and done. So the hard thing with polarity is almost everybody wants to say, so as long as it's this, then it's always that, and I never have to think about anything other ever again, right? And there's a problem with this because we can always ask y'all if something has polar bonds and if it's a polar molecule. We can always ask you about those bonds. So even though I'm going to say some things that will help, you still need to be able to do the analysis. So when we look at all the potential options, if all peripheral, that means outside, non-central, peripheral, I think I'm misspelling that, peripheral atoms are the same, and we're dealing with and no lone pairs and no lone pairs, then you're gonna have a non-polar molecule. Not making any promises about those bonds, but a non-polar molecule overall, because as long as everything's exactly the same, no matter what your bond angles are, all of your bond angles, all of your polar bonds will cancel out if those dipole moments exist. So if all the peripheral atoms are the same and you have no lone pairs, then you should have a non-polar molecule. Sorry, this is allergies, by the way. Also, this is talking for however many hours. Once you're down here with dealing with lone pairs, there's only 2 times square planar and the 2 linear options. These might be non-polar because these are the only times where the lone pairs cancel. One of the things that, sorry about that. One of the things that all of these other shapes have is they have some sort of lone pair somewhere on the molecule, and these don't cancel each other out. So all these little ones I'm circling. So the thing is that all these other ones have lone pairs that do not cancel. So that means that all of these, bent, trigonal pyramid, seesaw, bent, T-shaped, square pyramid, T-shaped, all of these are actually polar. Now again, we're not talking about any of their bonds. They're polar because of the lone pair. So there are some things in your analysis of a molecule that can help speed you up, but realize that if either the atoms are not the same around the central atom, then you have to figure out what's going on. Or if we've asked you, does the molecule have polar bonds? Yes, no. And is the molecule polar overall? Those are 2 separate things that you then also have to consider. So I know oftentimes for polarity, people would like the quickest answer. And sometimes if the only question is polar yes, polar no, or polar versus non-polar, sometimes that can go a little bit faster with some of this. But do just keep in mind that there are different ways to ask that question that might require a more in-depth analysis. So just keep that in mind as you guys think about polarity. Okay, my hero. Sorry, my husband just brought me a milkshake because he's amazing. Also, I meant to get a snack between teaching and my exam review, and I didn't. Also, I wound up having to go home because I forgot my tablet at home. So anyway, milkshake. What was all that for? Dipole moments. Oh gosh, that was all for dipole moments. Yay. This is for the deviation thing. I'm gonna answer that one. So one thing I do want to comment on, so I'll still do them. Don't get me wrong, I'll still do them. But that's 9 questions off of the fall 22 exam that I've been asked to do. These are probably, yeah, they're 1 through 28. Those are all multiple choice questions. 9 out of the 28 multiple choice questions is more than a third of the exam. So I don't mind doing this, but this is a lot. So for people that are looking at the fall 22 exam and having problems, I need to remind y'all that we have a peer tutoring center. So I will still do these in the follow-up video. If I didn't already say this, I will still do these in the follow-up video, but we have a peer tutoring center that's in the basement of the library. And we also have the chemistry clinic that's hanging out in Berkner. I apologize, I always forget the room number, but the room number is on the syllabus. It's on the front cover of the syllabus. The peer tutoring center is in the basement of the library with the big glass windows. So I will still do these. I will still do these, and I'm happy to help y'all. It makes me a little nervous that I've got requests for 9 questions out of 28. That's a lot. If you really don't understand how to get the answers for 1/3 of the questions on the fall 22 exam, that's okay. That's a really good place to start studying, but that also means that just watching me do it is probably not enough. We probably also need to do some end of chapter questions and get some more help on that. Because that's more than a third of the old exam. Just FYI. Bond angle deviations. So, because this got asked about twice. So bond angle deviations, there's 2. So first of all, for bond angle deviations, as far as power of repulsion, whenever I think about this, I always think about the word repulsive, which here we are talking about the fact that electrons are negative and they repel each other, other things that are negative, but I also think about the word repulsive, like ew, gross, repulsive. I don't want to be around that. So I keep thinking like something that's going to be like smelly or gross. My kitchen after I have not cleaned it in a long time. So this goes with a lone pair as being the greatest, and then a triple bond, and then a double bond, and then a single bond. So we could just ask you about this idea of basically where is there more electron density, because that's really also what this is ranked as. This is also really ranked as a greater electron density. To less dense. That's really the other rating scheme that this has. Most of the time, the reason why we care about it is because we're either going to do things like in that ammonia molecule that we looked at earlier, where here's my lone pair and here's my bonds. And that lone pair essentially, because that lone pair is a pair of electrons, but it doesn't get to go in between nitrogen and hydrogen, it's just stuck on the nitrogen. It's going to essentially repel against those single bonds a little bit more. So those single bonds are basically going to squish together more than they would have if that lone pair had been in a bond. So in here, this should be that less than 109.5. We could also look at this, that molecules. Dr. Diekman actually put this one on the 701 page. It's also linked in my notes. Your real molecules. Yeah, NH3. Bond angles. Whoa, it's hard to read. So we always just do less than 109.5. But you can also see the actual bond angle if you really were curious about it in my shape. Versus, yeah, methane. So here's methane CH4, no lone pairs, all nice and evenly distributed in between, so perfect tetrahedral geometry. Ammonia, where you have that lone pair squishing our bond angle essentially into less than. Does this have something with a double bond in it? Not that I can use. Darn. That's okay. I forgive it. So that at least gets me through the lone pair part. The other part I'm going to have to draw. So honestly, we typically focus on the double bond after this. It would still work for a triple bond. So if we had something that was large enough where we could have, I'm going to use A's and X's again. So if I had something that was like triple bonded to a carbon, and then I had, I don't know what this would be, something else down here, I would still have 3 electron domain geometries, and this triple bond then would have that same effect and would push my single bonds closer together. The difference here is now the bond angle in between my X's would be less than 120 degrees. But because this bond angle in here now shrank, I have another bond angle. I have another bond angle. It's up here. Whoopsies. I know. Why are you not happy with me? This over here would then be greater than 120. So some folks get a little bit uncomfortable when we start having to deal with greater thans. And there's a couple things about the greater than. One, we basically deal with greater than when we get away from lone pairs. So when we are dealing with just lone pairs are always going to be a less than game, because whenever we deal with bond angles, you know, I was doing pretty okay with my computer setup until I opened FET. We're going to get rid of FET and see if closing out of Chrome fixes my problem. Go away. Go away. Yes. Thank you. So keep in mind that whenever we say we have a bond angle, that is the angle between bonds, which means not between a bond and a lone pair. So I have to have 2 bonds to get a bond angle. We need 2 bonds. So we do not talk about the angle between a bond and a lone pair. That would be a lone bond-lone pair angle. We don't calculate it. It's not a thing that we look for. So the only time you have to worry about greater than is when we're dealing with bond angles, when we're dealing with triple bonds and double bonds. That's when we're going to start to think about this, is when we're dealing with triple bonds and double bonds. And really the reason is because since in this particular setup, we have this notion that everything is flat. So this is from it's the other reason why we often use a trigonal planar geometry to explain this. It's because it's a little bit easier when this flat version is real. This is actually planar, so it actually is in the page. And essentially squishing the two together here does create a larger bond angle on the sides. Also means there's also a larger bond angle over here. If we were going to ask y'all about this, keep in mind that what we would need to do on an exam is, if I had whatever this is, we would actually basically have it set up where we either go ahead and label, and we'd have A, B, and C, and we'd ask y'all for bond angle A or bond angle B or bond angle C. That's often how we do it. Sometimes we just ask for all the bond angles in the molecule, in which case you would mention both greater than and less than. So there's different ways to do this, but when you're doing deviations of bond angles, keep in mind that if it's lone pairs, it'll just be less than, we'll just shrink it. If you're dealing with single bonds or double bonds or triple bonds, then you actually have to worry about greater than or less than. And again, it's all about electron density. So the whole notion of all the bond angles comes from VSEPR, which stands for valence shell electron pair repulsion. And all we're really talking about is the fact that negative things repel each other. So the more negative stuff you have in one location, the greater the repulsion power. So a triple bond has 6 electrons hanging out in between 2 nuclei. It's going to be able to repel that single bond that only has 2 electrons in between the nuclei. Greater electron density, less electron density. Okay. So I've answered, there's another question, at least one more. So we did bond angles, deviations, bond polarity, and dipole moments. I have not talked about most of the other things. We did lone pairs because that was the same idea. Okay. Let me address the person who asked about equations. I have to admit that I have not checked the end of your chapter textbook, so I'm a little bit confused about what you're talking about, and honestly, most of that is my fault. So for the record, my confusion is mostly my fault. I want to acknowledge that. Because I know there's a couple of equations in the textbook that we don't cover, and I think that's what you're referring to, but I'm not certain. So honestly, the person that's curious about equations, this might need to be an office hour question, because I'm not confident that we're going to be able to communicate about this very well in the format that we've got. And I'm sorry about that. I may try to take a moment so that at least everybody knows what I'm talking about when I say, hey, I know that there are totally equations at the end of those chapters, but I haven't looked at them yet. So we're not necessarily going to do an in-depth analysis of those equations, but we can at least take a look at them together. Because we might just be talking about stoichiometry, which is kind of the math portion of that, but I'm not certain. This is good. Aha. So in ALEX, there is the textbook. I forget where it is on your screen. My screen's kind of complicated and has a bunch of extra stuff in it. But when you get to the ebook, it should be just in the end. It should be in the chapter. Ooh, key equations. Key equations. So yeah, chapter 7 just has this thing about electrons and bonding molecular orbitals versus anti-bonding molecular orbitals. This is molecular orbital theory, which we are not covering. So if this is the equation that you were describing, we don't do this one, because this is hanging out in chapter section 7.7, and 7.7 is not covered on the exam. It's kind of cool, it's kind of fun, but we're not doing it. So molecular orbital theory, not covered. You just need the bond order stuff that we've already talked about when we did resonance back in chapter 6. So if that is the kinds of equations you were discussing, then I gotcha. If that's not the kind of equations that you're discussing, then I either need you to put that back in the chat, or I need something. What's key equations for chapter 8? Oh, percent yields. We're not doing atom economy. Atom economy is not covered. Percent yield is. So percent yield is a real equation. Atom economy, no. Percent yield, yes. So those are the equations I thought you were discussing. I could be wrong. Y'all also see me try to write the questions down real quick. So sometimes by the time I come back, I don't have it right. So I'm going to check this one off like I answered it. And if the chat explodes because I did not answer the correct question, please tell me. We'll address it again. Or for the first time, since I did it wrong the first time. So I know I haven't talked about everything. But let me go ahead and see where we are with questions at this point. So if there's questions on some of the stuff that we just talked about, I don't get too far away. So any questions we have in the chat that are new?
Just one more.
Okay.
Does a dipole moment occur when bonded with H?
Okay.
And that's
it. Great. So this is where it very much depends on what's bonded to the hydrogen. So the thing is that you often get, I don't know why I spelled occur with an E, that's weird. So the thing with hydrogen is hydrogen's very small, right? It's a really small little atom. And it only brings one electron to the table. It doesn't have a lot of power behind it. So the thing is, you can get a dipole moment with hydrogen as long as the other thing is fairly electronegative. That's the whole concept behind the hydrogen bond, which is that whenever hydrogen is covalently bound to fluorine or to nitrogen or to oxygen, any of these bring so much more electron density to the party that you absolutely get a dipole moment in between the hydrogen and the fluorine, between the hydrogen and the nitrogen, between the hydrogen and the oxygen. So yes, you absolutely do get a dipole moment when different things are bound to hydrogen, just not carbon. So not carbon or hydrogen, but everything else, you'll absolutely get a dipole moment in that bond. No promises about the overall molecule because it depends. But yes, that hydrogen, because it's kind of not very good at bringing electron density towards itself, does actually form polar bonds with most everything else. Because it's not very good at getting electron density towards itself, so it does usually form polar bonds because of that fact. Everything else is usually better at it. Most other elements are better at pulling electron density away from hydrogen. There we go. All right. So I'm actually going to go ahead and hit up some of the properties of liquids. Some of these things I don't mind doing in the follow-up video, but let me go ahead and do some of the things we hadn't talked about yet, which are dealing with vapor pressure and surface tension. So vapor pressure and surface tension are both intermolecular forces, or both properties of liquids. So in general, whenever we talk about properties of liquids, there are 4 or 5, depending on how you want to count them. There's boiling point, melting point. I do kind of throw these into the same idea. There's surface tension, viscosity, and vapor pressure. This is the summary part. We're going to get into the big deal of why in a moment. For the first 3, as I've written here, the stronger the intermolecular forces, the stronger the property. Except for vapor pressure, where the stronger the intermolecular force, the lower the vapor pressure. So the 2 I got asked about were vapor pressure and surface tension. So we're going to talk about those. Surface tension first. So surface tension, this is the idea that when your molecules are all attracted to each other, they're going to form like a little skin on the surface of the liquid. This is not the best drawing, it's okay. And essentially, this is the reason when it rains, you get raindrops, they kind of form droplets. If you had lower surface tension, you'd have this kind of like ooched out thing that we don't see very often because we usually see water. So high surface tension looks something like this, where it kind of beads up. This would be lower surface tension. And we're talking about in surface tension, the ability of those molecules to be attracted to each other so that the surface of the liquid holds together, essentially. If you've never seen them before, I'm going to try to find you guys a picture of insects. So if you don't like bugs, you might just shut your eyes for a minute and I will tell you when the bug picture goes away. Water strider bug. So these are what are called water strider bugs. And I don't know if you guys can see this, but it's sitting on water. So all these little divots in them is the water strider bug being on top of water. And it can do this because of surface tension. So surface tension is the entire reason that this little insect hangs out on top of the water. All surface tension. So that's what that is. I'm gonna make the bug is gone. So for those of you that did not want to see the insect is now gone. It's safe again. We're back to me drawing pictures. So the whole notion of higher surface tension, higher intermolecular forces, it's the more those molecules are attracted to each other, the more that surface of the liquid can essentially be strong, or can be all together, can be one thing, even though it's a liquid, right? We think about a liquid and like we go straight through those things. But surface tension will control how a liquid acts, how its properties are. And so surface tension just controls what the surface is doing, what the interplay is between the top of the liquid and the air typically around it. We are assuming that there's air around it, that we're not in a vacuum. That's another story for another day. So that's surface tension. Hopefully that helps. Vapor pressure vapor pressure is different. So all the other properties of liquids are trying to describe the liquid. Vapor pressure really is going to describe the gas that a liquid forms. So if this is my liquid, there's going to be some amount of evaporation. I'm going to assume that by this point in your lives, you have been around enough liquids, or especially water, to know that things do evaporate over time. So in this case, we are talking about the fact that liquid will evaporate, and vapor pressure is going to measure the gas above the liquid. So this is really the reason why that property of liquid seems backwards, because all of the other properties of a liquid, the stronger the attraction, the better something was able to be a liquid. And all the other properties are written, the better a liquid it is, the better, or the stronger, the property. This one is about the gas, which means the better a liquid this stays, the worse it's being a gas. I hope that made sense when I said it out loud. The better, stronger, supposed to be an R in that word. The liquid, the lower the vapor pressure, because it's a gas, or it's describing the gas form. So essentially, the vapor pressure is how well does your liquid evaporate. And when you think about this, the stronger your intermolecular forces are, if you have really strong intermolecular forces and you have really strong attractions between all those molecules, you don't get a lot of gas out of this. You get low evaporation because all of those molecules are hanging on to each other. And because they're hanging on to each other so tightly, they're not going to go into the gas phase. They're going to stay a liquid because they're attracted to each other. They like being a liquid. Being a liquid is great. Strong intermolecular forces. So low vapor pressure. But if we have low intermolecular forces, those molecules are not hanging on to each other very well. The more of them go into the gas phase, the more you get in the gas phase, the higher your vapor pressure is. So all of the properties of liquids with intermolecular forces, it's all about the fact that the stronger your attractions between molecules, the better your liquid stays a liquid. True no matter what. It's just vapor pressure technically describes the gas given off by the liquid. So vapor pressure describes, it's still a property of a liquid, but it's describing the gas part that came off of the liquid. So it seems a little bit backwards. No. We did vapor pressure and IMF, and we have surface tension. I'm going to do some math. So we haven't done any of chapter 8 yet. We got 45 minutes left. Time to do chapter 8 stuff. See what happens. So someone asked about complicated chemical reactions. I'm going to remind you that you have the end of chapter questions. For balancing. And I'm going to really cross my fingers. There used to be one in there that was particularly awful that we would never put on an exam, but I think it's gone now. Gosh, I hope it's gone. It was balancing. It was one of those where like it has like multiple parts, like A through G, and A through F are great, and G is like terrible, hard, complicated. So I'm going to give you an example of one. Ooh, I know how to make this worse. but fair game worse. I'm going to type this out and I'm going to make it bigger. Here's a way. Here's something you guys will not like, but technically is fair game. Here we go. So I'm not confident that this is getting across what the person who wanted to know about complication was. And that's part of why I said, oh, we could look at the end of chapter questions for a good amount of complicated. Because this is the one that I came prepared with. And then I realized we could make it more complicated by giving it to you all in words. So for those of you who may have forgotten, your polyatomic ions are fair game from now to the end of the semester. Once we taught you polyatomic ions, always fair game. So the fact that this says sodium phosphate, yes, you do need to remember what phosphate is. So we could give it to you all in words. So let's break this down for a minute. Sodium phosphate reacts with calcium chloride to produce sodium chloride and calcium phosphate. Okay, so here's my to produce, which means that's my arrow. That means that everything on this side is going to be a reactant. And everything on this side, which it wrapped around, is going to be a product. So first of all, I can do that part. So I need sodium phosphate. Got that fabulous periodic table that I have scribbled all over. Big shocker. Here's sodium in A, alkali metal. So +1 charge. With my phosphate, phosphate's got a -3 charge. So therefore I need, so this was my original one. So therefore I need 3 sodiums to go with my 1 phosphate. Calcium chloride. Calcium is over here. 2, so it's got a +2 charge. Chlorine, I scribbled too much. There we go. Chlorine's over here, so it's got -1 charge. So I can bring this back. Calcium should be a +2. Chloride ion be a -1. So this is plus CaCl2. Yields, produces sodium chloride. Good news, I got all of my charges already. So now I just have sodium and chloride. So that will be NaCl plus my calcium and my phosphate. Ca3 PO4 2. I know no one's excited that nomenclature still matters, but nomenclature still matters. I'm glad we had this chat now rather than later. Yeah, for that. I wish I'd written just a little bit smaller. No. So, oh no, I do have to do that. Was like, do I care that I wrote it so big? I actually do. I need to make this just a little, actually I'll just rewrite it. So it's just a little bit smaller so that it all fits on one screen. I tried to leave myself space to put in coefficients, which was nice of me, but now I can't see everything. Yeah, looks like that. So for balancing a reaction, what I want to do is I'm just going to go from left to right on this. So here's sodium and here's sodium. And I've got 3 sodiums here, so I'm going to need probably 3 here. I'll try that. I have 1 phosphate here. Oh, but I have 2 phosphates over here. So I'm already wrong. So maybe I start this over again, because that's already wrong. So one thing that can help when you're looking at these is trying to figure out what things are going to be easier to deal with at the end. Yeah, practice. Honestly, it's not so bad. This is the second thing ever. So I've got 2 phosphates here. So I'm going to need 2 of these. Now 2 times 3 is 6. Now that's a 6. Then my calcium here, there's 3 of those. If I put a 3 here, I still have a 6 for the chlorine. 3 times 2 is also 6. So what I'm doing is I'm looking at these, and I've got sodium, phosphate, calcium, and chloride ions. And basically I'm looking to see now at the end, I have 2 times 3, which is 6 on this side. I have 6 times 1, which is 6 on this side. Phosphate, I have 2 times 1, which is 2 on this side. I have 1 times 2, which is 2 on this side. Calcium, I have 3 on the left. I have 3 on the right. And chlorine, I have 3 times 2, which is 6, and 6 times 1, which is also 6. So I've got the same number of atoms on both sides, same number of each element. You know, I also noticed I didn't get to change, I didn't get to add anything. So all the stuff that's in black is the chemicals I had to work with. So when I was doing this balancing up here, I don't get to add anything to this reaction. I just have to deal with whatever they gave me. So no adding extra reactants or extra products, none of that. Now we have this, what can we do with it? Many things. I'm gonna work in moles first, because then I don't have to get masses. So one of the things that I can do is I can ask if 7.2 moles of sodium phosphate react with an excess, we are going to start with an excess of calcium. I'll make this bigger in just a minute. How many moles, so we're going to do moles of sodium chloride are produced. So let's make this bigger so that y'all can actually see what I wrote. Step 1. So this is still going to go off of the same chemical reaction. So this is assuming that we are working with this chemical reaction we've already drawn. So we are assuming that we are still working with this in all of its glory. So I'm just going to copy that and move it down here. Lovely, wonderful. So one of the things that should strike you when we're looking at this new question is it asks me to start with sodium phosphate. It told me that I get an excess. And then it asks how many moles of sodium chloride are produced. So anytime something tells you that you have an excess, excess means all you could want and more. All you need and more. So you don't just have enough, you have an excess. You have extra, more than you need. Really, this sentence in blue is actually there to tell you that we are actually going to ignore calcium chloride. We have plenty of it. We are not going to run out of it. We got lots of it. No need to worry about it. So we're just going to focus on our sodium phosphate to our sodium chloride. So we're going to start with sodium phosphate, and the goal is to move to sodium chloride. So we're going to start with those 7.2 moles of sodium phosphate. And then we're going to use our balanced chemical reaction. So when we do this, I'm going to use the reaction. Whatever I have up here, moles, I need the same thing down here. So I have moles of sodium phosphate, so I need moles of sodium phosphate. from my balanced chemical reaction, I can actually use all these coefficients as moles. So I'm going to put a 2 right there. So 2 moles of sodium phosphate, 2 moles of sodium phosphate. That's what I started with in our moles of sodium chloride. 6 moles of sodium chloride. So whenever we're using the reaction, this is always in moles. So my reaction is always in moles. So whatever this ratio is always going to be in moles when I'm pulling from the chemical reaction itself. So I just pulled and I used my stoichiometric coefficients. That's how I got that. So all I'm going to do now is divide by 2 and multiply by 6. And that gets me a grand total of 21.6 moles of sodium chloride. So math thing number 1. So when we're looking at these, because the chemical reaction is all in moles, that means that whenever we give you something in moles and we ask for moles back, you might notice everything was in moles and there are absolutely no grams in any of this yet, right? No grams. And this is the answer to the question. The question asked us, it gave us moles in the first place, asked us for moles at the end. If that's what's happening, because the chemical reaction is also in a mole to mole ratio, that means we don't have to do grams at all. More often, these questions begin with grams and end with grams, and we do moles in the middle. But that would be a different kind of question. So that can still happen, but that would be a different question. But here we just began with moles, ended with moles, moles in the middle, moles all the way down, instead of turtles. Okay, so I know there's still more questions, but it's almost 6:30. And I know I talked about both balancing reactions and a little bit of math. So I'm going to go ahead and pause for a moment and ask if there's any more questions in the chat.
Just one more.
Okay.
Are there going to be any balancing questions in all words on the exam?
I have no idea. So good news, bad news. So it's fair game. I will say that, like, it's completely fair of us to ask you to do that. So it is completely okay. It is completely fair game. Y'all should remember how to make compounds based on their charges. And this one only has 1 polyatomic ion in it, and it's off of your polyatomic ions list. So this is a beautiful example of something that I would not feel bad about putting on your exam at all, because it's nomenclature stuff that you are responsible for, and I would be fine with putting that on your exam. So is it on your exam? I'm behind. I was supposed to take a look at your exam questions before this, but I have not done that yet. I'm in a little bit of trouble because I need to at least read through all the questions, if not do your entire exam between when this exam review is over and 9 p.m. tonight. It's fine. It's fine. I have time. So yeah, so it's fair game. Nomenclature, fair game. Writing out something all in words and asking y'all to balance it, fair game. Are we going to do it? I honestly don't know. Didn't look yet. Are we allowed to? Absolutely. Absolutely allowed to. So I'm just going to extend this question that we just looked at one more round. So if we were doing this question, but what if we kept moles in the beginning, but we put grams at the end? How many grams of sodium chloride are produced? I just changed one word. And honestly, we're going to use the stuff that we just did. I'm going to rewrite it. Also, I need my reaction back so that we don't forget where things are coming from. I do keep scribbling more things on this reaction. It's getting a little messier as time goes on. That's normal. So I still haven't given something in moles, but now I want grams. So we still start this off the same way. Moles of sodium phosphate. And I'm still going to use my balanced chemical reaction. So I still need moles of sodium phosphate, and this is still going to go to moles of sodium chloride. All of that's still going to be the same. So 2 moles down here, 6 moles up here. Same idea, because we're still going to go from here to here. They're still from 2 to 6. But the difference now is if I ended here, like we did up here, that would only land me in moles. And that's not now what my new question has asked me for. Now I need grams. Well, if I need grams, this is that part to remember that your entire periodic table is essentially in grams per mole. So what I can do over here is take my sodium. I've got 1 sodium at 22.99 and 1 chlorine at 35.45, and I can add them together to get the molar mass of sodium chloride. So this total thing is 58.44 grams per 1 mole, just to write that out in a different way. Since that is 58.44 grams per 1 mole. Copy that. Bring it back over here. Paste. Because what I'm going to have, so still whatever is up here goes down here. So that's moles of sodium chloride. So I need moles of sodium chloride down here. So in 1 mole of sodium chloride, I have 58.44 grams. So now I can just add this step. So 7.2 divided by 2 times 6 times 58.44. And we could have done this stepwise. So we could have also done it one at a time and taken the 21.6 moles that we got before and just multiplied that by our molar mass. That'll also work. There we go. Grams sodium chloride. So that at least gets us into grams. So a reminder that y'all will still need to be able to go from grams to moles and moles to grams. You need to be able to do both directions. So we did a balancing chemical reactions. We've done a little bit of stoichiometry. Let's go ahead. Oh, actually, hold on. Let's do percent yield while I'm here. So I got some grams, percent yield. What happens if you did this in the lab? And in the lab, you recovered only 998.2 grams of sodium chloride. What is the percent yields? So percent yield is the actual divided by the theoretical times 100. We're going to write that all out. So first of all, it says in lab. So this number here is the actual, because it talks about in lab. Should you actually do the lab and actually get stuff, whatever you recover is your actual in lab. Whatever you find, whatever you isolate, whatever you measure at the end. This number up here in blue is what we determine as what we call the theoretical. This means basically that the math says so. The math says so. So it's not a real number that you got in real life, but you did all the math and the math said, this is how much I should get in the end. I don't know if you've ever had this problem with like young siblings where like you make cupcakes or like something happens and the little siblings are like, but this is what it should be. This is what everything tells me should happen. And you're like, yes, but this is real life. So theoretical is the what should happen. If you followed the recipe exactly what the recipe told you should get, but real life is sometimes not always as good. Or sometimes you eat some of the cookie dough, so you don't actually get a dozen cookies, you ate some of it. Don't eat your lab experiment. Also don't eat raw cookie dough, also bad. So we're gonna put the actual divided by the theoretical. And multiply by 100%. 8.2 divided by. So this then becomes 0.7908 times 100%. So we get 79.08% yield. So whenever we do percent yield calculations, oftentimes the actual is less than the theoretical. Occasionally it can be more. It's more common that the actual is less, but if you get like 103% yield, double check your math so that you didn't flip something upside down accidentally. But it is possible to get over 100% yield. Usually what happens in real life is whatever you were doing was probably wet, like it was an aqueous something and you needed it to dry completely and it didn't dry, and then you get more than 100 because everything's wet. Water weight. So that's percent yield. The thing I was gonna, I know, I was like, what was the other thing I was gonna do? Yeah, let's do this one. Okay. Given 5 grams of hydrogen and 30 grams of oxygen, how much water can be produced? So, first of all, we have a chemical reaction, but is it balanced? So, I was telling my class this today. If you're given something with no coefficients, this right now has no coefficients, you need to be skeptical and be like, is it balanced? Or is everything just 1 to 1 to 1? So 2 hydrogens and 2 hydrogens, that looks okay. 2 oxygens and 1 oxygen, oh no. I need 2 oxygens, gets me 2 oxygens. Now I have 4 hydrogens. Now I have 4 hydrogens. Now we're balanced. So if there's no coefficients, be skeptical. Take a look at it. If there were already coefficients, you may trust them. So if there's already coefficients there, you can trust them. If there are none, then be skeptical. Think about it. So 5 grams of hydrogen, 30 grams of oxygen. How much water can be produced? We'll say in grams. So what's happening here is we have numbers for both reactants. So we have numbers, we have values for both reactants. That means that we actually have to deal with those numbers. So this is going to give us something that's called limiting reactant. So one of these 2 things we should run out of first. I don't know which one, but one of these things we should run out of first. So whichever one we run out of first will control how much product we can actually produce. The analogy for this usually involves cooking. So for example, if I want to make a bunch of sandwiches, but I only have 2 pieces of bread, I'm going to run out of bread really fast. So if I've got like a giant stack of cheese and I want to make grilled cheese sandwiches, but I only have 2 pieces of bread, I am not making a lot of grilled cheese because I'm going to run out of bread very quickly. And so the bread's going to control how much I can actually make. That's really the idea of percent yield, or the idea of limiting reactant, is whatever you have less of will usually determine that. But the tricky part with less is we mean less in a mole-to-mole ratio kind of a way. Let me walk through this and see if we can get us there. So what I'm going to actually do, there's a lot of different ways to do limiting reactant. I'll show you the way I like to do it. So this whole thing is one reaction or one recipe. This whole entire thing. So what I'm actually going to do is I'm not going to worry about the water right now. I'm just going to figure out how many reactions or how many recipes I can make with 5 grams of water or 5 grams of hydrogen and with 30 grams of oxygen. So I'm going to take my 5 grams. And I'm going to go from grams to moles. So if I'm going to go from grams to moles, I'm going to take a look at our periodic table. I have H2, so therefore I need 2 times 1.008. This is going to be 2.016 grams of H2 in 1 mole of H2. And then I'm going to go from my hydrogen to reactions. That's what I'm going to do. There are many different methods of limiting reactant. This is the way I do it. So in 1 mole, not in 1 mole, I use whatever is in the reaction. 2 hydrogens. 2 hydrogens. 2 moles of hydrogen is in my 1 reaction. So I'm not worried about products right now. I just want to know how many reactions, how many recipes can I make overall. I'm going to take my 5, divide by 2.016, and then divide that by 2. And I can make 1.24 reactions. So if this was a cupcake recipe, I could make the entire recipe 1.24 times. I don't know how many cupcakes that actually makes me, but I could do the whole recipe. I could do the recipe with my hydrogen that many times. I don't know how much oxygen I have. So let's check on the oxygen. So if I have enough oxygen, there we go. If I have enough oxygen, I could do 1.24 reactions with all the hydrogen. So if I have enough oxygen to react all the hydrogen, this is how far I can get. Let's take a look at the oxygen. If I have 30 grams of oxygen and periodic table, 16. So 2 times 16, 32, for my O2, 32 grams in 1 mole of oxygen. And then in my whole reaction, I give 1 mole of oxygen for the whole reaction. I'm looking at the coefficient that's not listed there, but there is 1. 1s are invisible. I have 1 mole of O2 for my 1 reaction. So if I could react all of my oxygen, I could make 0.9375 reactions. So that's how many reactions I could get if I can use up all of my oxygen. Now, you can see that I have 2 different numbers, but they're both in terms of reactions. So both of these are in terms of reactions. One of them assumes I got to react all the hydrogen. The other one assumes I got to react all the oxygen. But the thing is, only one of these numbers is correct. So the correct number is going to be the smaller number. And here's why. This is back to my bread and cheese example. If I only have 2 pieces of bread, but I've got like 20 pieces of cheese, I'm only going to make 1 sandwich with my 2 pieces of bread. Even if I have a lot of cheese, I've got so much cheese, I have so much hydrogen. Hydrogen says I can totally go to 1.24 reactions, no problem. Look at all the hydrogen I have. But oxygen doesn't have enough. I don't have enough oxygen to make as many recipes as hydrogen does. So oxygen is going to be what we refer to as the limiting reactant, because it's the one we're going to run out of first. It's the thing that's going to control how much we can make. Now, because we took all the time to calculate this number, what does the problem ask me again? What did I ask for? How much water can be produced? So since we took all the time to calculate this number in reactions, I'm actually still going to use this number. So I can actually still take this number, 0.9375 reactions. And then what I can do is I can say in 1 reaction, I'm going to look at how many moles of water I can make. So in one of this whole thing, I get to make 2 waters. I'm using the stoichiometric coefficient in front of that. I can make 2 moles. Sorry, I want to have the word moles in there. 2 moles of water. So that can just tell me how many moles of water I can make. That's in moles. The question asked for grams, not very eloquently, but it's in there. So I am going to go back to my periodic table, find hydrogen, 1.008, and oxygen. So 2 times 1.008 plus 16 should get me 18.1016 grams per mole for my water. So I can go back, and we could have done this all in one line. Moles water, and in 1 mole of water, I have 18.016 grams. Shoo. So that's my final answer. Limiting reactant problems are longer than not limiting reactant problems because there's typically more calculations you have to do because you have to deal with both reactants. So one of the things I would recommend as y'all get ready for the exam on Saturday is be able to recognize a limiting reactant problem and just know that that's probably going to take a little bit more steps to get to the answer. It doesn't mean that it's a harder problem. It just means that it has more steps to it. So it might be a little bit longer to do. So you might consider doing that one not first, because it might take you a little bit longer than some of the other questions. So it's just something to consider. You don't have to follow my advice, but it's an option, because limiting reaction problems do just typically have more calculations in them. So good news, while there's always another way to ask questions, we did at least cover one of every type out of chapter 8. It was only one, but we did do a balancing question. We did do we started with moles instead of grams, but we did do just a stoichiometry problem that involved excess. We did do a percent yield calculation. And we also did a limiting reactant calculation. Again, there's more than one way to do limiting reactant, and there's more than one kind of question you can ask about limiting reactant, but we did at least do an example of each. I know there's not a lot of time left over, but I'm going to go ahead and see what questions y'all have and see what I can answer over what I just did. But first I'm going to scroll back. Where is my list of questions so that I can add to my list? Here's my list of questions. Oh, brother, where did it go? Okay. Are there other questions like that are being asked in the chat?
There are actually no other questions that we have.
Whoa. Okay. Well, that makes my stuff a little easier. Okay, so other things I think I answered. Balancing complicated chemical equations. So I tried to give you an example of what could be complicated. I definitely understand the idea, because oftentimes in class, we will try to do things that are somewhat straightforward. Realize that when it comes to balancing for the exam, the question still has to be doable in a fairly short period of time. So I'm still going to say for balancing complicated ones, to look at the end of chapter questions, because I definitely know what you're getting at, but I also don't know how to give you enough examples to kind of narrow down like how complicated is complicated. But I definitely understand the feel for like what is exam worthy. We did a mass and grams balancing reactions thing. We did those. Things we haven't done yet. So there's a question about hybridization, and basically I think what's like, when do we bother hybridizing things? So in general for hybridization, grabbing this thing. So for hybridization, anytime you're focusing on a central atom, and you need one of these geometries, you're dealing with hybridization. So hybridization, as far as when do we bother hybridizing, it's basically going to be when you have more than 2 atoms and your central atom then of 3+ atoms is going to always be hybridized. So what I mean by that is you can sometimes get away with not hybridizing if there's only 2 atoms together. So if I want to just deal with like a fluorine bounded to a fluorine, this, because it's a single bond, I really don't need hybridization for this. I can just have 2 atomic p orbitals overlap for my fluorines. Everything will be fine. Or dealing with 2 hydrogens bounded to each other. This is also fine. I don't need to have hybridization for hydrogen. So a lot of times if it's a single bond, we don't always need hybridization if there's only 2 things present. But if it's a central atom kind of a thing, I'm trying to think of a good example. Oh, here's one. I've drawn this before. So The thing is that because when we think about hybridization, we're also thinking about electron domains. This central atom here must be hybridized because we expect to have this 120 degrees. If it's actual, it's less than, because of the double bond. So that carbon has to be hybridized. Your hydrogens do not need to be hybridized. Because they're just hanging out with their little 1s electron, they'll overlap just fine. So the tricky one comes when you want to think about this oxygen. Oh, what's going to go on with the oxygen? Now, the thing is that the argument I'm going to make about the oxygen is in order to get a double bond and the double bond oriented correctly, so that the double bond is going to have shared electrons over the space, I'm going to make the argument that your oxygen needs to be hybridized. Because of the double bond. Because I need so many electrons to go in the same direction for that hybridization to work out. So that one does get to be a little bit more of an iffy thing, like what about that peripheral atom? But if it's a double bond, triple bond, it likely still needs to be hybridized so that all of our geometries can still be in place. Because the truth is that if we had pointed out the oxygen and asked how many electron domains does this one have, we still would have gone with this being in a 3 electron domains, which is still going to be that trigonal planar, even though 2 of them are lone pairs. So my argument's going to be that for this, it makes more sense to say, even though this is a double bonded oxygen, that since you have 3 electron domains here, that's going to be better described as having hybridization. So most of the time, you're actually going to assume that your atoms in general are usually hybridized, because it even makes oftentimes the lone pairs make more sense. But your hydrogens basically don't need to be hybridized. A lot of times your fluorines, because they're also on the outside with 1 single bond, probably don't need to be hybridized. For the most part, we're going to be focusing on central atoms. So the main things to keep in mind are like your hydrogens basically are not going to need to be hybridized because they're just going to be little 1s electrons hanging out. Oh, am I on the right page? But it's a good question. It's an interesting question to consider. When do we hybridize? When do we not hybridize? Okay, I am pretty much out of time. So things I'm going to be doing in the follow-up video. These questions off of the old exam, which will go last. I'm also going to be talking about the hybridization for carbon and phosphorus, which I'll probably do first. And then I'll talk about induced versus instantaneous dipole, which will lead me ever so very well to talk about London dispersion forces. And then I'll end with the questions off of the old exam. And unless there's anything new out of the chat, that's all the questions. Are there any new questions out of the chat in our last minute?
Oh, there's not.
Hmm?
This is all we have.
All right. Okay. Then in that case, I know it's only 6:59 according to my clock, but that's close enough to 7 o'clock. And there is definitely not enough time for me to cover any of these other topics in 60 seconds. So we will end it there, and I will make the follow-up video probably first thing in the morning. Maybe tonight if you're real lucky, but probably first thing in the morning.
All right. Well, thanks so much, Dr. Taylor, for joining us this evening. Just some information about the follow-up video and the recording of this. They will all be posted to the Living Learning Community's YouTube channel sometime tomorrow morning, tomorrow afternoon. As soon as those links become live, they will be shared with Dr. Taylor, who can pass them all along to you. So feel free to use this video, the follow-up video, to help you with all of your future studying. Thanks so much for joining us. We hope that this was helpful, and I hope you have a great rest of your evening.
Fabulous.